welcome to this webinar on the design fundamentals of an anaerobic continuously stirred tank reactor. I'm Paul Green, and I run a biogas advisory business. We hold these free monthly webinars for their educational content. Today, I'm pleased to have one of the North America's leading providers of biogas digesters here with us, PlanET Biogas, to talk about the CSTR, the workhorse of the biogas industry. The slides from today's presentation are available on my website, green-tech.com/events. You'll have an email tomorrow with the link. We'll get to your questions at the end as time allows. With that, I'm pleased to introduce Nils Hirsch, Vice President with PlanET Biogas. Nils, the floor is yours.
Yeah, thank you, Paul, for the introduction. Hello, everybody. It's a great pleasure for Jelena and me to present here about design considerations for CSTR digesters. CSTR, as Paul said, it's continuous stirred tank reactors or complete mixed digesters, more commonly known. I'm responsible as Vice President in North America for engineering, procurement, and sales, and I'm actually will be playing only a very small role here in this webinar. I will introduce a couple of minutes the company, and the real star of this webinar will be Jelena Gligorovic. Jelena is an extremely knowledgeable application engineer with our team, and she will talk in more detail about the design considerations following me. A couple of words about myself. I'm a mechanical engineer. I have an engineering background. I come from Germany originally, as some might have heard from my accent. Or actually, everybody, I guess. I tried to polish it out, but I never succeeded, so I gave up. I came actually already in 2015 to North America, and I started working with a tidal energy pioneer. It's generating electric power from ocean currents, and I was always drawn to renewable energy, and then started 2019 with PlanET here in North America. And PlanET checks off a lot of the boxes that are important for me in professional life, right? Working in a sustainable sector, doing something important for the next generations, being an innovator, and a company small enough to be agile, but big enough to be taken seriously as key player. And PlanET is a key player, a large supplier, leading supplier for anaerobic digestion and renewable natural gas technology with a large footprint here in North America. So how do you become a leader in your field? You build many, many plants, and that's what we've been doing. We have been building biogas plants. Next slide, Jelena, please. and learned step by step, right? You do mistakes here and there, you correct them, you learn from them, you optimize, you get better one step at a time. And we've been doing this for 25 years, and we are now approaching a 4-digit number of biogas installations worldwide. So I strongly believe that a company is defined by its values, and moreover, how does it live its values? And PlanET was founded in 1998 by 2 engineers with a farming family background, not the 2 guys here on the slide, different ones. And they started building biogas plants for their family and friends. And you don't want to mess that up. And this customer focus is ingrained in the PlanET genes till the current day. And for the 2 founders, climate protection was extremely important. And CH4 emissions reduction is such a powerful lever, such a powerful tool to tackle climate change. And that's a big, big motivation for every single team member of PlanET. And I hear that in interviews all the time, right? Yeah, we would like to join the good cause, right? Do something for the next generations. Respect, right? Respect is listening to the client, listening to the customer requirements, open and frank communication, collaboration, right? That's key. And I'm often asked, okay, what makes you unique, right? Why should we go with PlanET? There are so many biogas companies around there. Why should we go with you guys? And I mean, for one, it's a wealth of knowledge and experience, but far more important is if we do not have the right technology, we will tell you. If we are not the right company for your project, we will tell you. But if we have the right technology, if we are the right company, we will work as hard as we can to provide you with the best solution for your project, considering all project requirements, OpEx, CapEx, the entire lifetime to make it a successful biogas project. And that's a value addition. That's a value addition that we provide. Okay, the next slide falls a little bit under the motto leading by example. So this is a slide of the headquarters in Germany, built in 2022. It's designed as a carbon neutral building using a bunch of different renewable energies. So geothermal, solar, wind, there's electric vehicle charging, and of course RNG. So let's have a look at our footprint in North America and what we are doing in North America. We have been opening our doors in 2006 in North America, and we have installations from coast to coast. And right now, 33 operational plants, 14 biogas plants in construction, and 3 subsidiaries in strategic locations in Colorado, New York, and Ontario. And on top of that, we have more than 55 dedicated and well-trained staff to design, deliver, and service your projects in North America. If you have a project in North America, service technicians from us won't be far away. Okay, let's just have a very small glimpse on design considerations, and Jelena will talk far more about that in the following. There are 3 keywords for me in design consideration. One is flexibility, and then modular and standard. To provide the best solution, you need to have more than one option. And one example is concrete and steel tank systems. Both have advantages and disadvantages. What defines if a concrete tank or a steel tank is the right way for your project is the project requirements, right? For instance, is winter construction, flexibility regarding winter construction important? How does the infrastructure look like? How does the infrastructure supports concrete construction? Is local content a requirement? So all those questions will define and will help us to define what's the right solution for your project. Second keyword, standard. Technical container is one example. Plug and play module. So it's a little bit exaggerated. It's a little bit more work involved to install it than plug and play, but it's pretty easy to install on site. It's a key component containing pumping manifolds, heating manifolds, MCCs, electrical. And our philosophy is make it as easy as possible to install on site, shift fabrication into fabrication facilities into a controlled environment. And then at the end, this allows us to choose from proven standard components to tailor a solution that fits your project best. So to become a leader and to maintain being a leader, you have to be always a step ahead of the game. And it's very, very important that you have a strong R&D department and a strong research going on in the company. And this is just one example. PlanET is working on an automated steering technology, AI-based. So basically, camera is monitoring what's happening inside the digester to detect problems early on, right? Formation of floating layers or foaming events, and then to activate automatically countermeasures. Makes the operation safer, aims to make the operation easier, and as a frosting on the cake, in most cases, it will reduce the energy consumption as well. So last slide before we get to Jelena. And that brings me back to 2019 when I prepared for my interview with PlanET. I didn't know anything about biogas. I wanted to work in renewable energy. So I decided, okay, it might be a good idea to learn a little bit about biogas before that interview. So I started my research. my first thought was, well, biogas makes sense, right? It's baseload suitability. And moreover, it looked pretty simple. It's like a pot of soup. You heat it, you steer it, produces gas, right? But that feeling only lasted a couple of minutes. And then I got into more details and I, oh, wow. Yeah, there's a lot of biology going on. Looks like you need a lot of experience to deal with that and to design good plans dealing with that. And then I came across a diagram that looks, or a figure that looks a little bit similar to this one here. And then I saw the whole picture, right? Wow, this is pretty complex. You can produce various different energy forms, heat, electric power, RNG, different forms, CNG, LNG. You can produce bio-CO2, fertilizer. You solve waste problems. You need to get rid of the digestate. So this whole picture got far more complex. And this is key now, and that's the theme for the next slides from Jelena as well. It's extremely important to develop the right concept in the early project phases. In those phases where you play with mass balances, where you do simulations, where you do testing, sampling, where you sit on whiteboards, where you conceptualize your plans. Those are the phases where you actually have most flexibility to do modifications, to change, to adapt. Later on, with each single step, it gets more and more expensive. You don't want to change drawings. You don't want to do changes in detailed design. It gets worse in fabrication. When it's finally installed, it will be very, very expensive. So you have to focus on the early phases, key. Analyze our requirements. And that's where PlanET is extremely good at. So now I hand over to Jelena. Jelena, the scene is yours.
Thanks, Niels. Thank you for the introduction. So my name is Jelena Todorovic. I have a background in mechanical engineering as well. My specialization when I was in school actually was biomedical devices, but similar to Niels, I really wanted to end up in the environmental sphere and work in renewable energy. So I found myself in anaerobic digestion and haven't looked back. I've been in the industry since 2019, and I've been with PlanET for the last 2.5, almost 3 years now. Starting in the project engineering department, working on agricultural and food waste projects, and then now in the applications department, working on the business development side with proposals and feasibility studies and stuff like that. So as a part of this presentation that I'm doing here, I have the agenda up on the board, but as Niels touched on, I want to focus on the major design considerations for digesters, which includes more of the process design as well as technology considerations as well. So maybe focusing on the process side first, and then considering technology with the tank considerations, mixing systems, heating techniques, some common issues with sand, grit, H2S, and then circling around to operability, safety, and a case study at the end. So my goal for this presentation is to provide an introduction into AD systems, and then to identify what information is critical for the process design and technology. But first, I want to look at project feasibility from a holistic perspective, and to touch on what are the most important considerations for determining a project's feasibility. So starting here, if you look at a project kind of as a bullseye on a dartboard, the feedstock and offtake agreements are kind of the outer circles of the project. The site logistics, getting the site, all of that would kind of be the actual circle. And then the inside, the core of the project is the project feasibility. So I want to touch on all three of these a little bit here. So the first important part of establishing a project is getting a site for the facility and ensuring that the logistics of obtaining and using that site are taken care of. So this relates to permitting, zoning, and land acquisition. Something that also needs to be taken into account here is the site's proximity to its feedstock, i.e. the waste producers, and also the offtake, so like the pipeline and For example, the farms where there's going to be land application of digestate. Another thing that is critical for a site with respect to the logistics is the proximity to neighbors, whether that's other farms or industrial facilities, or even residential housing, which can be affected by any noise or odor or truck traffic that's happening with the site. So if you have that in order, the next steps are determining the offtake agreements and the process feasibility. So for the second item, I'm referring to feedstock agreements with suppliers of organic waste, whether that's agricultural or organic, like food waste and energy crops, or offtake agreements for biogas and digestate. Biogas offtake agreements are typically with utilities, industrial users, or energy companies, and the offtakes for digestate can vary greatly. So the lowest cost option is typically storage and land application of whole digestate, but then local nutrient regulations and agricultural practices can determine whether or not this is actually feasible. So the level of post-treatment can vary greatly from this land application to separation to drying to full nutrient recovery systems. So offtake agreements are very, very important here. It's important to obtain long-term contracts that outline quantity, quality, and delivery methods for inputs and outputs of the system, since this obviously very directly relates to the price stability of a project. There's also a saying that's quite common in the industry, people love to use it, but it's garbage in equals garbage out with respect to your process design. Not referring to actual garbage, but if you don't know what you're getting in the facility, it's extremely difficult to design a process in an effective manner that allows you to know what you're getting on the output and to meet the requirements for your offtake agreement. So these agreements are very critical to a project. I'm mainly going to be focusing on the third item here, the inner part of the circle, which is process design and feasibility. This does have a direct effect on the first two items. And I will be talking about considerations that are going to be made upstream and downstream of the digesters. But the core of the presentation is going to be focused on the digester component itself and then how to size and choose a digester. There's going to be less emphasis on the waste preprocessing, the biogas treatment and upgrading systems, and digestate treatment, but all these things play into each other. Overall, these 3 points tie into determining the overall CapEx and OpEx of the facility and ensuring the financial viability of a project. So well-structured feedstock agreements and offtake contracts ensure predictable revenue streams, and then an effective process design maximizes the efficiency of your biogas production and reduces operational costs while also increasing project scalability. Of course, assuming that you have the site that you're planning for your project. So as mentioned before, the first half of my presentation is going to be focused more on the process side and the design considerations that are required for the initial sizing of a digester and determining the outputs that you're going to get. So the factors that I want to cover are feedstock composition, organic loading rate, biomethane potential, retention time, temperature, nutrients, and pH, and how to use that information to determine your biogas and digestate quantity and quality, and how that ties into your digester sizing. Okay, so the first item here is feedstock composition, and mainly focusing on the dry matter content of your feedstock. I have a diagram that I made here on the right side, showing the breakdown of feedstock from your dry matter content downwards. The green square that I have around the top half of the diagram indicates what is typically the most important, what are typically the most important parameters for mass balance. And then the items at the very bottom that are not in that green square are important, but are not necessarily make or break in determining your biogas production or performance projections, but they are important for other pieces of equipment. So I did want to include them here as well. So for the feedstock, there is a proportion of water and total solids for each type of feedstock. Your total solids is your dry matter content. which is the amount of solid matter present. It's also referred to as TS. The typical dry matter content in feedstocks, I would say, is between 5 to 20%, depending on what the feedstock is, which can be a lot of water, 80 to 95% water in a feedstock. So you might think that you're making an effective use out of your digester volume if you have 80 to 95% water. However, we'll see in the later slides how loading rates and other limiting factors, which really determine how much dry matter content you can have in a digester, and how even the small amount is quite important. So in your total solids, that's broken up into your volatile solids and inorganic solids. Volatile solids being the organic fraction that can be decomposed during anaerobic digestion. This is essential for assessing the biogas potential and the organic loading rate, size of the digester, all of that. The inorganic fraction is pretty much exactly what it sounds like, which is the material that cannot be decomposed during AD. So this is your sand, your grit, your metal, and other items, ash, those kinds of materials. I did want to break it down and just mention that within the volatile solids and inorganic solids, there are subcategories, which are dissolved and suspended solids. So volatile dissolved solids and volatile suspended solids added together equal 100% of volatile solids. So these two do make up the whole component of the category above them. You can also sometimes hear total dissolved solids and total suspended solids. These are just the ratios of dissolved or suspended under each of the three main categories there. So dissolved versus suspended, you can think of it as if you have a glass of muddy water and you let it sit for a while, the mud settles at the bottom, but you still have brown water, unclear water above the mud that's settled at the bottom. So that mud that is at the bottom, that's kind of your suspended solids. And then the material that's dissolved within the water above, kind of what you can think of for dissolved solids. So this is not the focus during mass balances, but I did want to bring it up because it's an important aspect for other types of equipment. So for example, if you're using a separator to separate your solid and liquid fraction of your substrate or of your digestate, if you have a high amount of dissolved solids, it's very difficult for a separator to obviously separate that into solids and liquids. So this ratio of dissolved and suspended solids is important on other areas of the design, such as impacting the capture rate of your separators. So I did want to bring it up, although it isn't the focus here. One thing to take note of is higher volatile solids means more biogas. However, there are limiting factors. I also did want to mention that some contaminants can technically have a volatile solids fraction, but this doesn't necessarily mean that they're suitable for the digestion process. So for example, plastics have a volatile solids fraction. They can technically burn up, they can technically decompose under various conditions. This doesn't mean that you want any plastic in your digestion process. So there's different values. Not all VS is the same, and there's different levels of biodegradability between even good types of volatile solids, like between different types of feedstocks and such. So I did want to mention that as well. We'll be touching on it a little bit in the presentation as well. I did also want to say that you want to limit the amount of inorganics in your digester as much as possible, since this can take up space, cause sedimentation, equipment damage, etc. So when you think of contaminants, most contaminants are inorganic solids, and you want to remove them. You want to remove sand, grit, metal, and in order to do this, some level of pre-processing might be required on the front end of the digester. So for agricultural projects, this is more so on the sand and grit side, and then for organics projects, it might be more so on the plastics, metals, kind of like the typical contaminants that you see in like a green bin program. Okay, so next I wanted to touch on the loading rate, which basically determines how much volatile solids you can put into your digester. So you're probably going to hear the term organic loading rate, or OLR. The organic loading rate gives an indication as to how well a digester can convert the organic matter or the volatile solids into biogas. It looks at the amount of volatile solids entering the digester within a specific unit of time. The units are typically pounds per cubic foot per day, or in metric, kilograms of volatile solids per meter cubed of digester volume per day. Sometimes calculations can use COD or chemical oxygen demand instead of volatile solids, but that seems to be more typical in wastewater applications, and using this OLR with volatile solids is what I've always used in digester process design, and it will be what I'm talking about here. So having too low of a loading rate generally means that you're not using your digester reactor volume as effectively as possible for the production of biogas. While a high loading rate can overload your digester and lead to the accumulation of organic acids and volatile fatty acids. The reason for this is if you suddenly feed too many volatile solids into your digester, this can make the AD biological process a little bit front heavy on the hydrolysis and acidification steps. And then that bacteria can produce too many acids, which lowers the pH in your digester and prevents the methane producing bacteria from being able to convert the acids into methanes effectively. So it can really damage the biological health of your system. I do have here some rules of thumb. So ideal OLRs can vary depending on the feedstock and its composition, the temperature of your digester, and the reactor type. For PlanET's mesophilic CSTR digesters, the general rule of thumb is listed here. So 0.19 to 0.22 pounds per cubic foot per day for manure applications, and then up to 0.28 for organics projects. I'm going to be talking about how this is affected by co-digestion in the next slide here. So, of course, being able to push your OLR, having more volatile solids can lead to higher biogas production, but it also means that you may need less energy for heating because you have less water in the system, and you can also reduce your digester size, or basically have more biogas production per volume of digester, so less footprint, and save on CapEx. However, as I mentioned, you can overload your digester and have negative effects as well. So there's definitely a balance to ensuring that you're optimizing the size of your digester. I also want to note that calculations and design bases are they're not always related to, they don't always relate exactly to real world results. So this needs to be considered as well, and ensuring that you have a little bit of a conservative mindset as well in your design basis, understanding that what you have on paper may not exactly translate to what's happening in real life all the time. And accounting for any variations in your feedstock or any future expansions, anything like that is also critically important. At the bottom of the slide here, I do have a little bit of a scale here. So when you think of 0.28 pounds per cubic foot per day, I don't know about you, but that doesn't really mean anything to me when I see that number. So I have the scale here that for the organics number for the 0.28, that essentially translates to about half a cup of volatile solids in its dry form in 7.5 gallons of water. So you can see how a small amount of volatile solids can make a big difference here, and how important it is to focus the attention on making sure that you understand what you're getting in your digester, since small proportions can make a big difference here. Okay, so the next thing that I want to talk about is the biogas field model. I have a graph here on the left side. That is an example biogas field curve of a substrate over 28 days, showing the cumulative biogas typically when you send your feedstock to a lab, this is the kind of information that you receive back from them. So if you're not very familiar with reading biogas curves, essentially the retention time of a digester is modeled in the lab, and you'll see at the bottom it has days up to 28 days for the sample, and then the biogas production listed as a listed in liters per kilogram VS on the y-axis here. So to read it, you take the retention time, you read up and you look at the biogas yield at that retention time for the substrate. So I touched on it before, but materials have different levels of biodegradability, and they also have different biomethane potentials, or BMPs. And these curves are used to give an indication as to how much biogas a certain substrate can give you when you put it into the digester. They all have, it's critically important to understand your feedstock, and I would recommend sending any feedstock samples to a lab before you really get into your process design. You don't want to always rely on theoretical values, which may not have the same makeup or composition that you're working on with your feedstocks. One thing to note here is BMP curves can also be used to determine the balance between biogas production and your digester sizing. So I have an example here on the bottom left. So for this substrate at 21 days, the biogas yield is 567 liters per kilogram VS, and then at 28 days, it's 581. So the difference between these two biogas yields is about 4%. But the difference between the retention times, or the amount of time that it spends in the digester, is 7 days. So 7 days of retention time means a higher digester volume that you need to maintain, to keep the material in the digester for that long, and that also means a larger digester footprint. Or even if you need another digester to accommodate that volume of feedstock that you're bringing in and keeping for longer periods of time. So sometimes there's a conversation between what is your biogas yield at certain retention times and what is the best bang for your buck, essentially. So for this example, a retention time of 21 days with the capex associated with a digester of that size may be more effective than increasing the digester size for 7 days more retention time and only getting a 4% increase in your biogas production. So this is where the conversations around capex and opex can kind of play into the process design. Another thing to consider is that different types of material also have different base retention times. So I've put on the screen here some base retention times that PlanET uses typically. So 17 to 21 days we find is optimal for manure, about 30 days for organics, and 40 plus for energy crops, depending on what they are. So if you have a co-digestion project with, let's say, manure and organics co-digested in one digester, you may have to consider the difference in base retention times here. So typically you go with the substrate that requires more time. So this time, in this example, erring more on the side of the 30-day retention time. However, this can be a conversation. So if you have a very small proportion of organics in a very large overall proportion of manure, it might not be worth it to increase the HRT all the way to 30 days to accommodate the base retention with the organics, when you may get enough biogas kind of more accommodating to the base retention time of the manure, or somewhere in between. So again, this is where process design can vary with different feedstocks. So I have a quick summary here. I know I didn't talk with separate slides on retention time, temperature, nutrients, and pH, but I do have a little bit of a cheat sheet here, I guess. So I've listed some important parameters for process designs, mostly focusing on manure and organics instead of energy crops, but kind of touching on everything that we talked about before with the OLRs, the BMPs, which of course are variable depending on the feedstock, the base retention times, or the HRTs that we're kind of designed to, And then I'll focus on the temperature as well with when I talk about heating systems. So keeping it in the mesophilic range, 100 to 107 degrees Fahrenheit or 38 to 42 degrees Celsius. One thing that I did want to note is there are also limiting factors on nutrients and pH. So for nitrogen, we tend to try to keep it below 13 pounds per incoming ton of material, which is less than 6.5 kilograms per metric ton for metric units. And then on pH, between 7.2 to 7.8 is ideal for methanogenesis, which is the crucial step in the biological process for biogas production, while accommodating the other steps as well. I touched on it a little bit, but there are some other considerations for a mass balance or process design that should be considered for every project. So these are typically project specific. Some questions to ask yourself are there differences in operations that need to be buffered? So for example, if you have a 12-hour per day reception and digesters that are operating at 24 hours a day, does there need to be a buffering step in between that? Number two, are there any variations in the quality of the waste that you're receiving? So differences in contamination levels. And three, are there any variations in the quantity of the waste? So for green bin programs, for example, this can be related to consumer food waste habits. And considering the fact that you might get like a bunch of pumpkins after Halloween or a bunch of Christmas tree components after Christmas or those kinds of consumer habits that can happen with green bin programs. On the agricultural side, this is usually less typical to have a lot of variation in the waste. However, if you're misting your cows or cow pooling in the summer, that additional water that could be getting to manure streams that might need to be considered. So now I want to talk about the technology considerations. So first, the tank material selection between concrete versus steel. In general, the key factors in choosing between concrete versus steel digesters are durability, cost, resistance to corrosion, lifespan, installation time, ground conditions, mixer efficiency, and other items such as that. So for PlanET actually provides both concrete and steel digesters. Concrete digesters have several advantages. One notable advantage being the customization in the sizing, the flexibility in the sizing. Complete adjustment of height and diameter in a way that makes sense for the mixing system. And they also can be partially buried, which can reduce the overall height and the visual impact of the digesters, although this is affected by ground conditions and groundwater tables as well. These digesters can also have versatile placement of the mixers, and these mixers can be placed both internally or externally based on the preference and the efficiency considerations for the mixers. They're also quite good for piping runs, interior of the digester, and also co-digestion. So they're suitable for many feedstocks, manure, agricultural waste, food waste, and they can handle both monodigestion and co-digestion. On the steel side, steel tanks are usually installed faster. They are a little bit more costly than concrete tanks. However, they are easier to install in colder weather, in winter conditions. So depending on the construction schedule, this might also determine whether you go with concrete or steel. PlanET's digesters are typically duplex stainless steel. We usually do a cylindrical tank with a dome-shaped roof, and they also have mixing and heating systems similar to the concrete tanks. They're known for their durability, their corrosion resistance, their long lifespan, and they can also handle co-digestion and different feedstocks as well. The nice thing about our stainless steel tanks is it's quite modular. So we have a couple of different standard sizes. We have 2 diameters and 2 heights. This allows us to reduce costs on the engineering and manufacturing, since we have these standard sizes and are able to roll them out pretty efficiently and pretty quickly. That's something to be considered for stainless steel tanks as well. Both are important for AD, and the choice really depends on project scale, budget, feedstock characteristics, local construction pricing, construction schedules, and even just the preference of the client. I just have some photos here of the concrete versus steel tanks kind of in the construction process. One thing to note on the bottom photo here, you can kind of see the how we've had to protect the concrete from the weather conditions when it was being poured and cured due to the lower temperatures. This can be a little costly, so something to consider again for construction schedules and whether concrete or steel is preferable, but of course concrete is more flexible in the sizing and can be buried, so a number of different factors to think about here. These are some photos for the steel tank string construction. So in the top left photo, you'll see our jack system that we use to construct the tank. So we have all of the panels connected to the jacks. We install the bottom ring, we jack up everything, and then we start on the next ring down below. So pretty easy for construction, quick installation time there. The other thing I want to point out here is in the middle, top middle photo, you can see that we have our insulation and our liner on the inside. This is something not very typical on steel tanks. In this way, you can see the steel paneling from the outside of the tank. We also do offer epoxy coated tanks as well. And then the bottom middle slide is, you can see the roof strapping going towards the center mast. The green mesh that you see on top is our eco cover, which we'll talk about in the H2S section. And then this is the roof installation process you see here. I do see a question about whether concrete's cheaper. Let me just go back here. So the steel tends to have a higher material price, but this is impacted by local contractor and material pricing as well. So typically steel is a bit more expensive on the material price, but it does have a shorter installation time. So sometimes labor pricing can make a difference as well. I also did want to talk about the selection between tall versus pancake digesters. So tall, obviously, being a tall tank, and then pancake digesters kind of being shown with the larger diameter versus height ratio on the right side photo here. So typically pancake digesters have the domed roof. Sometimes, most of the time, tall digesters don't have the capability to have the domed roof on top. And may require external gas storage. So for tall digesters, you get a higher liquid volume for a given footprint. There is less gas storage within the tank typically if you have the if you don't have the gas membrane cover, but you can have an insulated roof in that case. So that is a pro of the tall digesters, and you can also have a bit more mixer electrical efficiency with the tall digester. However, for biogas, for pancake digesters, there's the integrated biogas storage with the domed cover. And with this double membrane roof, there's also integrated H2S production, which we'll talk about with the biological desulfurization later on. There's also lower static loads on the soil, which can be quite important depending on the ground conditions of the project. And these pancake digesters can also be easier to clean since you can remove the roof to get into them. So I did want to talk about the gas membrane roofs separately here. So the dome shape that you see with an inner membrane and an outer weather protection membrane allows for several hours of gas storage within a tank. It depends on the feedstock and the amount of biogas production that you have in a tank, but I think typically we see around upwards of 6 hours of gas storage within a tank. If you have an emergency shutdown or anything like that, and then obviously if you have multiple tanks, your overall amount of gas storage increases. So with this flexible inner membrane and gas storage, you can get continuous flow to your RNG upgraders, which is definitely a pro of having the double membrane roof. And then with this continuous and stable flow of biogas, the RNG upgrader can then run at its optimal efficiency curves. And this will ensure that you have your consistent high quality RNG with lower electrical consumption, since your compressor VFDs can be run at optimal levels. The gas storage also allows for temporary storage of biogas in the event of a grid shut-in and prevents unnecessary flaring of good biogas, which of course means you're losing money if you're flaring good biogas, of course. PlanET also uses a system where rejected RNG can be flashed back into the gas storage dome to be processed again by the upgrader, which again prevents it from having to be flared and having to flare partially upgraded RNG as well. The digesters can also be cleaned out and inspected by removing the roof. So the roof can be removed within a few hours, and it can be reinstalled within a day as well. They can be rolled back and lifted with a crane if you need complete entry into the tank, and if you need partial access, it can be folded in half to allow access to a particular side of the digester, for example, without removing the whole roof. So talking about the importance of mixing in AD, so mixers are crucial components. Without proper mixing, you don't get uniform nutrient and temperature distribution, and you can also get stratification in your digester where the solids settle at the bottom and have sedimentation, and then you can also have floating layers at the top with scum, with plastics, and can also promote if you don't have good mixing, it can also promote foam production as well. If you have sediment at the bottom of the tank, this reduces the active volume of your tank, which can cause your biogas production to decrease and also increases your O&M with your digester cleanouts, equipment maintenance. There are also some dangers with improper mixing. So if you have improper mixing and a crust forms over the top of the digester and you're still producing biogas underneath, this can create pockets of biogas underneath the crust, which can be quite dangerous. And if they suddenly rupture, you can have a large volume of biogas suddenly going to the headspace of your digester, which can cause problems with the volume and the pressure. And of course, heating distribution is also promoted by proper mixing as well, which helps distribute the nutrients, maintain your temperature uniformity, and enhances the efficiency of the digestion process as well. So there's different, there's active mixing, there's also passive mixing. So passive mixing would be like plug flow and lagoon digesters. These are more prone to settlement, which also results in more frequent tank cleanouts for these systems. There are different types of active mixing systems. So there's mechanical, which are like paddle mixers and agitators. That's what PlanET typically uses, and that's what's shown on the bottom here. There's hydraulic and also gas mixing as well. The PlanET uses the mechanical agitators since they can handle high solids applications, and they can be adjusted to move, or at least the internal ones can move different levels of the tank, and can rotate as well to address areas of concern at the bottom and the top of the tanks. They're also pretty energy efficient. They may have some internal components that require maintenance, but there's also options to have external shaft mixers where the motors are accessible from the outside. So that's the right photo there. So that one is easier for maintenance there. Gas and hydraulic mixing isn't used by PlanET since it's less capable of handling high solids applications. Sometimes they require more complex tank designs, and they have other considerations for operability. For example, for gas mixing, they typically require a good amount of biogas in the headspace that can be recirculated for mixing purposes. So it's a little bit harder on startup and commissioning for those kinds of systems. One tool that PlanET uses for mixing considerations is CFD, or computational fluid dynamics. We look at CFD to visualize and predict the behavior of the fluid in our tanks with our mixing systems. It's typically used to analyze fluid flow in AD systems as relates to mixing systems, although I think it can be used for heat transfer analysis as well, although we look at it for our mixer analysis. There are limitations to CFD, mainly between the differences between what you get on a computational basis versus what you get in real life. So again, garbage in equals garbage out. If you don't know what your feedstock is, what the viscosity is, what your variations in your feedstock could look like, It reduces the accuracy of your CFD analysis. There are also a lot of computational resources required for CFD, and the models can be pretty complex and require calibration and validation. The benefits are cost reduction, so you don't need as many trial and error experiments. You can have some process optimization, and you can also identify risk areas of your tanks as well, and areas for improvement. So CFDs are usually used as an indicator of how a mixing system is doing, and not the end-all be-all of how it will actually perform in real life. So for a mixing metric that we use is any velocity higher than 0.1 meter per second is considered well stirred. The example that I have is for a hydrolysis tank with sludge in it, and so you'll see the areas of red with the mixers. That is right where the mixers are, and then everything. The middle of the blue is the 0.1 meter per second. So this tank is considered well stirred overall. And then again, this also doesn't account for shifting the mixer location to accommodate different areas of the tank as needed, which we can do. So a little quick visual. On the left here, I have just an example showing what you see when you look inside a window of a digester. On the left is a digester that's not like actively being stirred at the top of the tank. And then on the right side, you see what it looks like when a mixer turns on near the top of the tank and how effective it can be for breaking up any floating layers. The videos are a little bit blurry. I apologize. It's hard to film into the window of a digester. Okay, so we touched on temperature before, but I do want to talk about it now in detail. So maintaining the appropriate temperature is essential for making sure that the anaerobic microorganisms responsible for breaking down the matter are producing biogas and promoting the better quality of digestate as well. So there are different types of bacteria cultures that can grow under different conditions. We typically use mesophilic, which are 35 to 40 degrees Celsius or 95 to 104 degrees Fahrenheit for our tanks. Since mesophilic temperatures provide process stability with a higher diversity of microorganisms compared to, let's say, thermophilic, and it's also a lot easier to maintain the heat required in colder temperatures with a mesophilic digester than with thermophilic one, where you require higher heat input. So there are different heating techniques. Obviously, the first line of defense is your insulation on your tank to reduce any heat loss. And then you have external versus internal heating systems. So external would be like an external heat exchanger where you take the substrate out of the tank, put it through the heat exchanger, and then put it back in the tank. For internal systems, you have in-wall heating, heating loops, heating racks. So there are pros and cons for each. So there's a greater heat loss for the external systems, although they do require less internal maintenance on the tanks, inside the tanks. And then for internal heating systems, they're more efficient for heat transfer. They have reduced heat loss. It can be a little bit more difficult for maintenance. One way to mitigate that is to perform regular maintenance and checks during digester cleanouts. Typically about 80% of the heating is used to heat the actual substrate, and then 20% to account for any heat losses. And then heat recovery is also really important as well. So I'm going to talk about that. Next slide. So it's a great tool to minimize your OPEX and with a slight increase in your CapEx costs at the beginning of a project for associated piping and heat exchangers. So on one project that I'm working on, I just showed a bit of the process flow diagram here. We have a pasteurization system downstream from the digesters. So the output of the pasteurization system, which is at 162 degrees Fahrenheit, 72 degrees Celsius, we use that to preheat the material that's going into the pasteurization. So that's at 104 degrees Fahrenheit coming out of the digesters. This reduces our boiler load that we need to heat the material for pasteurization. Since there's still heat in that output from the pasteurization system, we also use it to preheat the material going into the digesters. which is at about 68 degrees Fahrenheit or 20 degrees Celsius. So this is a two-step heat recovery process. Implementing this requires more upfront CapEx and also considerations to the site plan. So how far is this equipment from each other? If your pasteurization system is really far from the input into your digesters, this might not be feasible. So these kinds of considerations are really important in the process design and when you're thinking about doing in your preliminary engineering. This can also affect your CI score and environmental benefits as well if you have heat recovery. So some challenges I want to talk about, the challenges of sand and grit. So sand and grit, I think I touched on before with the sedimentation at the bottom of the digesters. This relates to decreased AD performance. So you get a reduction in your operating volume and therefore your biogas production. I have a little drawing at the bottom there to show basically the reduction in liquid volume in your tank if the bottom portion of your tank is all filled with sand and grit. And then this reduces the amount of retention time that you have, or the amount of time that the substrate spends in your digester, and therefore you get less biogas production out of it. The other challenge with sand and grit is increased maintenance costs as it clogs pipes and equipment and causes damage to mixers and heating systems sometimes, and also difficulty in removing it. So you need to do a digester clean out to get rid of the sedimentation at the bottom, and then sometimes it can be difficult to dispose of the material. This digestate laden sand that you have there, it can be quite costly to dispose of it at a landfill or other facilities, for example. So how to get rid of sand and grit? The first step is, can you remove the source? So for example, sand bedding is quite typical for agricultural facilities. We try to encourage any farms to switch to fiber bedding if they're using sand bedding to remove the source of the sand. There can also be sand in organic systems depending on how the collection process is. So for example, if your green bin program accepts leaf and yard waste and people are scooping up leaf and yard waste, they're picking up a lot of sand, a lot of dirt, a lot of grit. So the first step is to see if the source can be removed, if any changes can be done to mitigate the problem before it even gets to your facility. There's also mitigation upstream of the digester with the use of pre-processing systems. Those could be sand separators, grit classifiers, hydrocyclones, and sedimentation tanks. One thing to note is using equipment upstream, it might have its own requirements. So for example, some hydrocyclone systems require a total solids of 12% to go into the hydrocyclone, but if your material is at 16%, this might mean that you need to dilute it and add water into the system to get it through the hydrocyclone before it goes to AD. So there's always considerations to be made on the actual pre-processing systems that you use as well, and choosing between them. And then the third way of mitigating it is with regular maintenance, so inspections and cleanouts. It can be quite difficult to know if your digester is accumulating sediment unless you notice a reduction in your performance over a longer period of time. So this is why it's important to use data collection to understand the trends and patterns. And if your input stays consistent but your biogas production goes down, that's kind of an indicator that you might need a digester clean out. So I want to talk about the challenges of H2S. So H2S, of course, has health and safety risks to humans and operators. It is it's heavier than air, so it goes into low-lying areas, which can be a danger for operators. It has environmental effects. It can help produce acid rain. It has an effect on the environment as well, and there are typically regulations on the emissions you can have for H2S. It's highly corrosive with damage to pipes and equipment, and can also reduce the quality of your biogas with the heating value. So reducing H2S is definitely a big concern for AD systems. There are two ways I'm going to be talking about reducing H2S. One of them is biological or in situ desulfurization. This is very cost effective and low maintenance. So essentially, oxygen injection introduces small amounts of oxygen into the anaerobic environment, which promotes the oxidation of H2S to less harmful components. And then even in anaerobic digesters, small doses of oxygen can create microaerobic zones where aerobic bacteria can thrive. The way that PlanET does this is we have our green eco cover net, which I mentioned before. This provides a surface for aerobic bacteria to propagate. We typically spray the net with the manure or the substrate during start of commissioning, and then the aerobic bacteria grows on the eco cover and provides us this culture that converts the H2S and the biogas into elemental sulfur, which then drops back into the tank. You can see that actually on the right side of the screen, that stuff at the top, which looks like stalactites in a cave. That's the eco cover with all of the bacteria on it, reducing the H2S in the tank. Obviously, you have to carefully monitor your oxygen levels, though, to make sure that they don't get too high and that they're not too high for the grid thresholds in your RNG with your grid specifications as well. However, this is a very cost-effective, low-maintenance way of reducing H2S. The other way is chemical. So PlanET offers Micronox, which is a micronized powder with iron oxide, hydroxide, and other functional oxides developed to be added into a digester. There's also ferrochloride systems, which we use as well in our projects. So the difference between Micronox and ferric, Micronox is typically dosed upstream in the pre-storage tanks and the manure pits. It's less corrosive, but it requires more time for the reaction to take place to see a reduction in the H2S. And it's easy to handle, it has easy storage as well. The ferrochloride is dosed directly into the tank since it's more corrosive. You do see a more immediate reaction in the H2S and the reduction in the biogas, so it can be good for spikes. But there are PPE and storage considerations that need to be made between the two. We do have a Micronox dosing calculator on our website as well. So typically one or more of these systems are used in conjunction with each other. So one of our projects, we have a three-pronged approach. So with the biological desulfurization, the Micronox, and the ferric, and we get down to less than 50 ppm of H2S of biogas in that project from a couple thousand in the biogas originally. So I will speed through these slides a little bit. I'm sorry, I will have them on the website. Just to talk about the considerations for operability in the preliminary engineering of our project. So I mentioned it before, but in the design, accounting for variations in your feedstock and your contamination levels, quality, quantity of your material can make a big difference on your process design and the operability of the project. You should also take care of what happens when there are disruptions to the process as well. So if your solids handling system is down, if you have a grid shut in and you're not able to inject RNG, what happens to your process? So for example, if you have extra gas storage with the membrane cover, that could be something to consider in association with these disruptions to the process. There should also be consideration for any future expansion. There should be consideration for ease of maintenance, so space for work, having redundant systems, standby systems, and then also accounting for a health and safety system, so ventilation, gas detection, emergency shutdown, that kind of stuff. In general, I recommend spending more time in design with operator feedback in your design sessions and your HAZOPs, doing lessons learned. And then in operation, making sure that you have real-time monitoring systems is essential for operability, and having data analytics to predict any potential disruptions. So like I talked about, if you know that your feed is staying consistent, but you see a slow reduction of biogas production over time, that could be an indication that your digester requires a clean out. So things like that to consider in design. And then of course, considerations for safety, which I mentioned before. So making sure that you are designing for safe biogas storage with pressure relief valves, which I'm showing on the screen here, and flaring systems to manage excess gas. Having adequate ventilation in enclosed spaces to prevent the buildup of gases, having gas monitoring systems for methane, H2S, CO2, and incorporating alarms and automated shutdown protocols. And then having designs for pressure control, so the pressure reliefs, the rupture discs, redundant safety systems to prevent accidents, and then regular inspection and maintenance of the pressure regulating equipment, as well as chemical safety, electrical safety, having intrinsically safe electrical equipment, proper grounding, and then of course having worker safety and making sure that your operators are well trained in the hazards of an AD plant. So I'll just go through this a little bit quickly here, but PlanET has service offerings. We provide engineering services, which I think Neil's touched on. We also have our own lab in Colorado, so we do digestive health testing, biological training, and consultation. We have technical services and commissioning support as well. We also have a tool, we call it our PlanET Academy. We use it first to onboard new employees and do training across the board on commissioning, electrical safety, biology, all of that. We kept it internal, and now we're offering it external as part of our operator training, and so having access to customizable content, online modules, all that's available with us as well. So a case study that I wanted to talk about is Dicklands, which is a project that PlanET worked on located in Chilliwack, BC, with feedstock being manure and food waste, and it produces RNG, fertilizer pellets, and clean water. I have a process flow diagram here, but I just wanted to mention that PlanET and with the Dicklands Farm project, it co-digests dairy manure, chicken manure, and food waste. The dairy manure comes from Dicklands Farm, which I believe has about 400 head of cow, and then also manure from neighboring farms, which is then pumped into the two 30x8 concrete digester tanks. The food waste, if it's clean, goes directly into the storage tanks. If it has contamination, it goes into the pre-processing system, which includes a depacker, a hammer mill, to remove any plastic, cartons, tin, paper, and other contaminants before it goes to the storage tanks. Dicklands accepts all kinds of food waste, food processing, supermarket, spoiled food waste, green bin, residential, fats, oil, and greases, animal feed, pretty much anything throughout the year. It co-digests inside the digester tanks, and then this biogas is upgraded into RNG, which goes into the pipeline as a substitute for the fossil fuel natural gas. PlanET's biogas upgrader, the Statoron M series 3-stage membrane system, is used here, which removes carbon dioxide, hydrogen sulfide, moisture to create a high quality RNG that meets the grid specifications for the Fortis BC gas grid. The capacity, I'm sorry, this is in metric, but it's 1,100 normal meter cube per hour nominal and 1,250 max. Sorry, I didn't put that in imperial. There's also 3 activated carbon filters, 1 for VOCs and then 2 in a lead live for H2S. The digest state here is interesting. So the digest state goes to sloped screens to capture large fibers, and then vibrating sieves to capture any small fibers. The liquid portion goes to mechanical vapor recompression, which separates the nutrients from the digest state by heating it to produce steam. And then once cooled, the steam turns into water, which undergoes reverse osmosis and is then used in the process as drinking water for the cows and as processing cleaning water for the plant as well. The solids from the slope screens and the sieves goes through a screw press to remove any excess liquid. And then this fiber and the nutrient concentrate from the mechanical vapor recompression are dried, pelletized, and heated to above 70 degrees Celsius for an hour to kill any pathogens before the organic pellets are sold as fertilizer. So PlanET's role in this project was the overall engineering, including the process design, site layout, process buildings, integration of third-party equipment, and permitting support. We integrated process equipment from multiple vendors, including our own PlanET equipment, into a design that meets the local conditions and is code compliant. We provided equipment for the 2 concrete digesters, depacker, pre and post storage tanks, slayer, and the RNG system, and provided construction and commissioning support. And we performed the role of the GC as well for the RNG system. And that kind of covers it from my case study, actually. So thank you, everyone. I think we can maybe answer some questions here, Paul. I don't know. I didn't leave a lot of time. I apologize.
I know. Great job, Yelena. You covered so much ground there, and I'm grateful to all the attendees. There's been so much participation in the chat and the Q&A, and we could go for quite some time addressing everybody's issues. I think the best bet is to just take note here of Yelena's email and give her, if there's a question that comes up, shoot it her way. And again, that was just a lot of ground to cover. So Yelena, thanks for the great job. Thank you for PlanET's leadership in the market. Appreciate your good line of products you make. And for all the attendees from literally around the world that are here, India, Asia, US, thank you for joining us. And next webinar is January 8th on hydrogen sulfide in biogas digester projects. So we'll thank you again, Yellen and Niels. Appreciate the opportunity and the support. And thanks to all the guests. And happy holidays, everybody.
Great. Thank you, everyone. Thanks, Paul.
Thank you.